Good afternoon, everyone. My name is Ali. With me are Ahmed, Mayada, and Laila. We are going to be presenting the final presentation for our thesis project, which is the automation of SoC design for IoT purposes. Our outline is as follows. First, we're going to give a recap of our idea description and project objectives. Then we're going to go in depth about the RTL generator. We are then going to talk about the floor plan generation. Then we're going to move on to the web application and GUI. Finally, we're going to update you about our overall progress and give a demo showcasing our product's main features. The problem was to develop a tool chain with automated design of SoCs in order to shorten the time to market. Our idea description was to build an open source commercial product that accepts the SoC requirements from a designer and generates a template based design, which implants such requirements out of the library of standard components. Our product is supposed to capture the requirements of the user by the GUI on the website and then translates them into a JSON file. This JSON file is then fed to the generator, and the generator produces the RTL description and the floor plan. Now my colleague Ahmed will talk about the RTL generator.
Okay, thank you, Ali. Now we're going to be talking about the RTL generator. But before doing that, let's just take a quick overview over the bus protocols that we support. First, we have the AHP Lite, which is a high-speed, high-performance pipeline bus that supports burst transfers. Now, every transaction on the AHP Lite consists of two phases, at least two phases. First, we have the address phase, followed by one or more data phases. Then we have the APB, which is a low-performance, low-speed bus, mainly used for low-speed peripherals. And lastly, we have the AXI4 Lite, which is also a high-performance bus. Now, our system currently supports or fully supports the AHP Lite and the APB, but it does not yet fully support AXI4, as we had started working on it and worked on the wrappers of the AXI4, but we have not yet fully finished the whole subsystem. Now, as Ali mentions, the JSON object of describes the SoC is passed to the RTL generator again, which produces the Verilog code for the SoC. So what exactly are the modules that RTL generator produces? First, we have the decoder that is produced based on the number of slaves and the addresses of each slave. Then we have the multiplexer. Then we have the default slave, the bridge in case of multiple buses, and finally the SoC top level. Now, what exactly is the default slave? The default slave is used in case of the master trying to read or write from an address in the memory location that does not exist in the memory map. That is when the default slave would issue an error signal to the master. Okay, so what we have here is just the generic design of an AHP system. This is what the user would practically input using the GUI. We have masters and multiple slaves. And to the right here, this is the system that our generator would ideally produce. As you can see here, the three modules in black, those are the ones that our generator automatically produces. Also, as you can see here, we can have multiple slaves, slave 1, 2, up to n, but we always have a default slave. As for the SoC top level, it is divided into 4 segments. First, we have the design information, the module name, and the port list, followed by the bus signals, followed by the instantiations of bus subsystems, such as multiplexers, decoders, bridges, or default slaves. And lastly, we have the instantiation of the masters and the slaves. So here are some examples that we tried out using different designs. So example 1 is just an AHP Lite. As you can see to the left, this is what the user would input using the GUI, and this is the JSON that would respectively get produced. As you can see here, this is the bus standard AHP Lite. This section right here corresponds to the master, and those 3 sections right there corresponds to the slaves, with each slave having different, of course, base addresses. After passing our output to Vivado and synthesizing, this is the schematic that is produced. Here we have the master, followed by the decoder, the 3 slaves, and the default slave, and lastly we have the multiplexer that multiplexes all the data from the slaves into the master. Everything here in blue, the blue circles, they reflect the modules that are completely generated by the RTL generator. Then we have the simulation. As I mentioned earlier, the AHP is a pipeline bus, which means that the data phase always comes at least 1 clock cycle after the address phase. As we can see here, for address 1, the data A1 comes 1 cycle after, 2, A2, 3, A3, etc. As for the F00, this is an invalid memory location. That is why the slave responds with the data deadbeef and issues an error signal over those 2 clock cycles according to the AHP error protocol. As for example 2 consists of just an AHP light and an APB bus. So we have 2 buses, and in this case, we're going to need an APB bridge. As we see here, we have 2 buses. One, this is the AHP light with ID1, and the second one is APB with ID2. This section again here corresponds to the AHP master, followed by the AHP slaves, and this section right here corresponds to the bridge. Now the bridge is considered a slave for the AHP bus, but is considered as a master on the APB1. That is why we have 2 connections unlike the others. Connection 1 with bus ID1 is of type slave, connection 2 is of type master. Again, using Vivado for synthesis and schematic, this is the output that is produced. We have the master, we have the decoder, followed by the AHP slaves, along with the default slave, which is this one, and the APB bridge, which is also an AHP slave, and the 3 APB slaves, and finally we have the multiplexer that multiplexes the output of the APB slaves along with the AHP bridge. Now, this is just a simulation of the following example to make sure that everything is working. We don't really have time to go over the details, but if you have any questions regarding the simulations, we can go through them in the Q&A period. Now, as for the last example, this is just an AHP light with 2 APB systems. So here, instead of 2, we have 3 buses. We have the AHP light of bus ID1, we have the APB bus ID2, and the APB, the other one is bus ID3. Again, this section corresponds to the master, followed by the AHP slaves. This one corresponds to the first APB bridge, and this one corresponds to the second APB bridge. Lastly, again, this is the schematic that is produced. Here we have the AHP master, the AHP decoder, the AHP slaves, APB bridge, the second bridge, the slaves corresponding to the first APB system, the slaves corresponding to the second APB system, and lastly we have the multiplexer that multiplexes all the data from the AHP slaves and into the master. Again, this is just a simulation to make sure that everything is working. We can go through over them if you have any questions. Now we leave you with Mayada to discuss the topic of wrappers and everything we've done in them so far.
Thank you, Afifi. So what are wrappers and why do we need them? If we have a slave that is not compatible with our bus protocol, we need to find a way for the slave and the bus to communicate together. This is basically what the wrapper does. It acts like an intermediate component, allowing a communication between the slave and the bus to happen. This is an example for an APB wrapper for a GPIO. As you know, the master, which is here the APB bridge, communicates with the bus, and the bus communicates with all IPs. In our case, the bus communicates with the wrapper, and the wrapper communicates with the GPIO. There is no direct communication between the GPIO and the bus itself. The wrapper basically transforms the GPIO into registers, these allowing the master to read and write from and to these registers. So in the JSON objects, we define these registers. As you can see here, there are 3 registers. Let's take the second one as an example. Its name is IO_DI. We have its description, its offset. The offset is very important because the master uses it as the address in which it reads and writes from and with. We have its size here, it's 8, and the axis is 0. Axis 0 means that it's an output from the wrapper, which also means it's an input to the GPIO. And we have its emission value. On the right side, you can see how it's defined or declared in the wrapper. It's an output because the axis is 0, we have its size is 8, and its name given. So for each register, we have an address, and the master uses these addresses to read and write from and to the registers. Let's have an example for how a master can write into a register. We define a selection line for each register. This selection is equal to the read enable ANDed with whether the P address is equal to the address of the registers or not, which means this selection will be high if the write enable is high and the address given by the master is equal to the address of the register. If this selection is high, then the register will have the value of the PW data, which is the data driven by the master. Also, one of the most important things that the Rapier does is mapping the signals that are not supported by the slave. Let's take the read and write enable as an example. The read enable value is equal to P selection. P selection is a signal that indicates whether the slave is selected or not, and with the inverse of P write, which is another signal that indicates whether it's a read instruction or a write instruction. So the read enable will be high if I'm selecting this slave and I'm reading, not writing. Same applies for the write enable, but it has an extra signal, which is P enable, which is another signal defined by the bus protocol. For the following components, ADC, timer, UART, GPIO, SPI, and I2C, we define the needed registers for our generator to generate wrappers for. So basically, these are the components that are not compatible with our bus protocols that we're supporting. However, we can add to this list as much components as we want, as long as we define in their JSON objects the needed registers. Now, Laila will walk us through the floor plan.
Okay, thank you, Mayada. Now we'll discuss our floor planning phase or part. As we know, the input of our SoC is this JSON object that is generated by the GUI. So our floor planning phase or algorithm starts by extracting the blocks and their interconnections from this JSON object. So this array of blocks and their interconnections is fed into the linear ordering algorithm. The linear ordering algorithm just kind of aims to minimize wire length. So how do we do that? It tries to arrange the block in a single row such that the wire length is minimal. So so after this, it outputs this linear order to the cluster growth algorithm. So the cluster growth algorithm aims to minimize the area. So it places the blocks one by one in the same order specified by the linear ordering algorithm. So that tries to make it grow evenly and achieve the smallest area possible. But the idea behind it is that if we pair this concept of minimal wire length and minimal area, so like if I'm trying to place two blocks that are next to each other in the linear ordering algorithm, then they probably the wire length will not increase by much. So the good thing about the cluster growth algorithm is that it's very fast, but it produces mediocre results. But we use it to generate or to produce an initial solution for a third phase, which is the heart of our floor planning process. So we use it to generate this initial solution used in a third phase. So what are the characteristics of our simulated annealing algorithm? So it simulates the behavior of material when cooling down until it reaches a minimum energy configuration. So in our case, we're trying to use it to reach a minimum cost configuration. It's iterative, but it's not a greedy algorithm. So it doesn't automatically reject a solution just because it's a worse cost than our current solution. So let's quickly go over details about the simulated annealing algorithm. So we have 4 parameters besides the initial solution. So we have beta, which kind of is a ratio representing how much importance we're putting or how much weight we're putting on the area versus the wire length. So if I use beta to be 1, it means all of my importance is on the area and I don't care about the wire length. So I don't want it to be used in the calculation of a cost. And because the simulated annealing algorithm aims to simulate the material when cooling down, we have an initial temperature, a minimum temperature, and an alpha, which is rate of cooling down. So basically, what our simulated annealing algorithm does is that it runs while the temperature is our current temperature is less than the minimum temperature, and it chooses 2 random pairs with each iteration, and it tries to move them. So it tries to switch them up. It tries to switch their places. It tries to move each one individually up, down, left, right, and then it chooses the best solution out of these 3. This becomes our trial solution. So if we are able to find a trial solution, because sometimes we are not able to do any of these move operations. So if our trial solution is not null, we check the cost and we check the cost difference. If the cost difference means that, or if our trial solution has a better cost than our current solution, then we automatically accept it. If not, there is a probability that we will accept it. This specific probability decreases as the iterations pass, or as the temperature decreases. So this means that in the beginning we are likely to accept any solution, even if it's a worse solution. But near the end of the iteration or near the end of the algorithm, the chance of accepting worst solution is close to 0. And at the end, we keep track of, with each iteration, we keep track of the minimum solution. So is the solution that I found better, or is it a global minimum in my floor plan? So at the end, the simulated annealing algorithm aims to return the minimum solution. So here, we're using example 2 that Afify discussed. Biggest component is the CPU, and then we have the slaves and the peripherals. So our initial area is 620, our initial wire length is 36.7, our initial cost is 386. After the process, during our simulated annealing algorithm, we can see that the cost is not strictly decreasing because we accept functions with worse cost. And then around iteration number 140, or 130, we see a sharp drop in cost. This is probably because we tried to move things around, and then just by a simple movement, we had a sharp drop in cost. But if we look right before it, we have a small hill. This is something we call hill climbing. Hill climbing is basically just something that simulated annealing is really good at. It's kind of getting through all the bad solutions that enable me to reach a really good solution. So this is exactly what happened. And we have the algorithm continues to run. And then our final solution has an area less than the initial solution, wire length less than the initial solution, and also the final cost is less, so 362, initial cost of 386. So now Ali will talk to us about the web application and our GUI.
I will now elaborate on how our web application is built. The front end of our website is made using the infamous trio of HTML, CSS, and JavaScript, and it is supported by Bootstrap to build a responsive and modular website. In addition, Font Awesome is used for all our icons. The back end of our application is built on Node.js and EJS, and the generators themselves are built in Python. As you can see here are a few sample pages from our website. However, we will showcase them more fully in the demo. I will now talk about our overall progress in the project. We are done with the generation of the RTL for the HV and AP protocols, supporting the 3 mentioned architectures and the necessary bridges. We are also done with our floor planning algorithm and capturing the requirements from the web app. Finally, we finished the generation of the wrappers for the AXI4 Lite. However, we could not finish the AXI4 Lite subsystem due to limitations posed by the coronavirus outbreak. The future work to be done is support Wishbone and its wrappers to implement the AXI4 Lite subsystem mentioned before, and lastly, to add further functionality to the web application. We will now present to you a short demo showcasing all of the functionality of our web application. Okay, let us now demo the website. As you can see, this is the homepage of our website. And if you click Get Started, it will bring you to the register or login page. And if you click Learn More, it will redirect you to the About page, which has some information about our tool. And there's the team page, which features us. And then if you click Login/Sign Up, it will take you also to the register and login page. And then if you want to register, you can come here and register an account. For the demo purposes, I'm going to log in with a dummy account. Okay, let's log in. Okay, when you log in, it brings you to the dashboard, and you have your designs here, and then you can create a new design. Let's create a new design. For the purposes of the demo, let's choose template 2, for example. And then now here you have the design editor. You can choose your master, slaves, and bus protocols. Let's choose the main bus protocol to be HV Lite, for example, and have the clock speed to be 100 MHz. And let's choose the peripheral bus to be on the APV, which has 50 MHz. Okay, let's choose the master to be the Cortex M0. And we can choose a slave to be a timer. And we'll give it a base address of 0x. And then we can save the changes. And then we can pick another slave. Let's make it an I2C and give it this address and save our changes. And then let's make a third slave, which, for example, we can make it a GPIO. And let's give it this address. Then, for example, this slave is unneeded in this design, so we can come here and then delete the slave. Here it's deleted. And then we can choose a peripheral. Let's, for example, choose an SPI. Let's give it an address of 4 zeros. Good. Let's have another peripheral. Let's make it, for example, UART. Then let's give it this address. We can save the changes. And these superfields aren't needed, so we can delete them. Now they're deleted. Now our design is complete. And then we have two buttons here, one to verify the design and one to generate the files needed. So now we're going to verify the design. What this button does is check that all components are specified and there are no components left unspecified. And it also checks that we have inputted correct addresses for every component that are non-overlapping and that can work together. So let's now verify our design. Okay, the design is valid. So we can close this, and now we can generate our floor plan and our RTL from this button. Okay, we're going to wait for it to generate, but since the floor plan takes a lot of time to generate, since it's a long algorithm, and it takes a lot of time through iterations, so we're going to cut the video and then come back when it's finished generating. Okay, we're back, and now the files are ready for download. Let's download the files to the desktop, for example. And then let's extract the files and open them. As you can see here, we have two outputs, one for the Verilog and one for the floor plan. When we open the Verilog output, we'll have all the files associated with the SoC. As you can see here, this is SoC4, this is the top module for the SoC. And here are the outputs and inputs, and here are the master wires and the slave wires. And then we have the default slave signals, the decoder signals, the MUX signals, and the bridge signals, and then the slave signals for the bridge. And then we have the instantiations. And because we're running out of time, I won't be able to go through all the files, but if you have any questions you can ask or want to see any specific file, you can see it in the Q&A session. After that, we have the output from the floor plan. As you can see here, we have a text file that contains the floor plan and the components. Each component has an ID, and this is the grid for the floor plan, and each number corresponds to an ID for each component. For example, one is the CPU and so on. Then we have an image for the initial solution given by the cluster growth algorithm. Here it is. And then we have the cost graph for the simulated annealing algorithm. The cost started at around 385, and then it was reduced to around 365 in the end after more than 200 iterations. And then we have the final solution image, which shows the final solution after running the simulated annealing. And that's it. That's all for the output. And now we're done with the demo. Thank you very much. Any questions?